But if we just draw a picture for this one, it's sort of like saying, okay, the rocket's going up and it's got a canister. It accelerates upwards at a steady given acceleration. And when it's a certain height above the launch pad, I don't know, let's call it 200 meters above the launch pad, it ditches this thing. So this thing initially has some upwards velocity. Maybe let's call it v1. But acceleration is just gravity, and it's going downwards. So it will eventually pull it back to Earth. But once it is disconnected, the only force acting is gravity. Okay, great. So how high is the rocket when the canister hits the launch pad, assuming that the rocket does not change its acceleration? Okay, so for a problem like this, there are sort of three important points in time. And this is almost like a notational or an organizational thing, but I'm going to try to show you how I would organize this problem. Because sometimes when you have like T1, T2, T3, and you get them all mixed up, sometimes even if you understand the physics, that can make the math really, really messy and might spit out the wrong answer. So I'm going to try to make this a little bit more formulaic, right? So we've identified the 3 points in time that are relevant. And the very first one is, I would say, at the ground. So when the rocket is on the ground, let's call this T1, or maybe T0. And then at the time of detachment, let me call this T1. The reason I chose 1 for V1 was because I wanted to call this T1 later. And then T2 is when the little canister falls back to the ground. Okay, so T0, T1, and T2. And with this in mind, what the first part of the question is asking us to find is basically how high is the rocket when the canister hits the launch pad, assuming that the rocket does not change its acceleration. That's basically saying the rocket has been accelerating the entire time, which is T2. So, and it was at rest initially. So the height is just equal to 1/2 a T2 squared. Yes?
I've noticed that this equation is used the most out of any other equation.
This equation is used more than any other? Yeah, sure. Right? This equation is basically saying when velocity naught is 0, you can just totally ignore it. Right? So that's all that's left is basically the squared term in time, which gets associated with acceleration. Yeah. So with that in mind, what else do we know in order to solve this, right? We have basically two unknowns, h and t2, sorry, I decided that I would use squiggly lines, right? H and t2. And this means that we need at least another equation relating these things. At least another equation. So the other one is going to be for the canister. It's going to say minus h is equal to minus velocity 1. Okay, really we have more than two unknowns. So this is going to get a tiny bit more complicated. But it's going to be the difference between T2 and T1 minus 1/2 g T2 minus T1 squared. And unfortunately, we just got to do a tiny bit of extra legwork to figure out what V1 and T1 are. I don't think that's too crazy, though, right? I don't think that's too crazy. Because they do tell us that the acceleration was at whatever, I don't know, let's call it 3 meters a second squared. And, the detachment happens, or essentially T1 happens when the height is at 260. So we can essentially figure out what V1 and T1 are, hopefully, by just saying, what is it like? Which equation should I use here?
Isn't it v final squared equals v initial
Vf squared, does this work? Minus V naught squared is equal to 2ax. Yeah, very good. So if this one is V1 squared and V naught squared is 0, well, we know a, and we know, I guess you would call this the change in height, which is h. So using it, very good. You got this faster than I did. But yeah, v1 will be able to tell us, so this will be able to give us an explicit value for v1. And as for t1, we should just be able to relate it by saying, what is it? v1 is equal to a times t1. So now that we know v1 and a, now we know t1 as well. So plug that in as you need to. Okay, so after that little diversion happens, all that's left are the two unknowns, h and t2. Very good, Xstacy. Thank you for filling in when I had a lapse. But do you see that problem? The whole idea is, like, you see this theme over and over again in kinematics, but when something is just a little bit too hard to solve with a single equation, well, then you just bring in an extra equation or two to try to solve for everything. Feeling okay with that?
Yeah, I feel like the struggle though would be like starting with like figuring out which equation to start with to find like the unknowns.
Yeah, okay. Maybe I
Like
can try to
trial and
talk about
error.
that a little bit more. Right, sometimes it is trial and error, but for, I guess just, I almost wish I could describe in words how I come across it. I feel like for most of these problems, I just instantly have intuition about which one to use. You know what I mean? Um,
Yeah.
Let me just quickly, maybe it would be helpful if I just pulled up on a screen the four kinematic equations. And so that at the start of every question, we can sort of go over which one seems helpful. Yeah, actually, it's going to be a little bit hard to do that with screen share, but maybe all of you can pull up the kinematic equations as you're following through, and we can
Yeah, I
discuss
have
at the
them
start
up.
of every problem. Okay. Oh, sorry. Did this problem ask for something else? Was it also asking about like finding the peak or something?
Oh, it asks for like the y, so the height, and then asks for the distance itself.
Yeah. Okay. So it asked for the height, and it asked. Okay, I got you. I've asked for the total distance. So the reason it's asking for the total distance is because going back to our picture, even after it's released, it's still going upwards for a while, right? So it's going to keep going up for a little while until its velocity kind of peters out, at which point it comes back down. So to do that, well, let's take a look at our kinematic equations. Yes?
Yeah.
So of the kinematic equations that we have, after solving this problem, we know what V1 and I guess T1 are at the moment of separation. And
Wait, so we're gonna have two different times, a time one and time two,
right.
or will they be the same thing?
So T0, T1, and T2 are sort of for the first part of the problem. And the time at which it reaches the peak is not any of these times. In fact, I'm hoping to just avoid talking about time for this, for talking about when it reaches the peak. I'm hoping to just use a kinematic equation that doesn't even involve time, because I'm kind of lazy, right? So of these equations, we do know the velocity at the moment it separates. We still know of the acceleration, or rather, sorry, the acceleration at this point is just going to be gravity, right? What is the condition for, like, can you simply describe a condition for me, like an equation, to describe what happens at the peak? Sorry, that was a very clunky way to word it, but I'm asking.
Oh, like at the peak so like when it stops, there'll be no initial velocity from zero.
Initial is the wrong
Right?
word, but correct,
Oh,
exactly. At the peak here, let's call this v at the peak, is equal to 0. So I think that strongly hints us to use the equation that relates the two velocities together, right? This is sort of
oh
vf and
yeah.
this is sort of v naught. And that's great for us because vp squared is equal to v1 squared plus 2a delta x. Excuse me, I guess this is maybe delta y, just because we like thinking about y being vertical. But we know this. This is just minus gravity, remember? And we know, we know this because this is just 0. So this is what we want to find. And this makes it very easy to do that. Yes?
Yeah.
So remember, this is the delta y that, describes its extra height after the initial
Oh,
260. So
oh
you just
okay.
have
So
to,
it'll be the answer for number one plugged into two. pretty much.
Sorry, say that again.
It'll be the answer we got for number one or part A for this question plugged into part B.
Yeah, yeah. How high is the rocket when the canister hits the launch pad? Sorry, I guess for part A, I should have reminded ourselves that once we find T2, we're basically going to want to plug it back into. Sorry, find H. I'm sorry. H is the height of the rocket once T2 happens, once the canister hits the ground. That H is pretty much unrelated to the maximum height achieved by the canister, which is going to be the delta Y we found from
Oh, okay.
this
I
part.
thought because you changed it to delta Y, I
Yes.
thought like it was like talking about the first one, but you just changed it because Y's respect like vertical. But that's
Yes.
what. Okay, I get it.
Yeah. Sorry, I think one of the comments that you made got me a little confused which part we were talking about. But yeah, you would just take this delta Y and then add that to whatever the height it was at the separation. And that's going to tell you how much how much its total height is on the way up. So then you'd probably need to multiply that by 2 to get the total height up and down, right? Or total distance up and down. Does that make sense?